Okay, in this part we are going to see the two main applications of standard deviation. And first of all, we call it standard deviation, which we use the notation EZ to stand for the term called standard score. And then you should have experienced the following scenario. For example, you've got 60 in Chinese and 70 in math. If you're just talking about the marks, sort of definitely you're doing better in mathematics. But But if you want to know whether you are doing better in Chinese or in math, comparing with your classmates, schoolmates in the whole form, and then the mark itself 60, 70, it doesn't tell you the reality. And then because you're comparing with the others. So that's why we need to use some ways so as to see how good you are in this 60 marks in Chinese and how good you are in this 70 marks in your mathematics result. So that's why we come to the term called standard score. Casually, you can say we are trying to find some ways. So using the same ruler, so that to compare 60 marks in Chinese and 70 marks in math, compare with your classmates. So the formula would be called EZ to be x minus x bar divided by sigma. And now you can see the effect or the meaning in the denominator. And first of all, x is your real score in a certain subject, for example, Chinese. Now you've got 60. And then next, you want to check with the x bar. That means the mean of the whole form. So this is the first part. Afterward, you need to know the dispersion of the result in the whole form. So in this way, we divide it by sigma, which is the SD of the subject of the whole form. Then you can have a term called standard score afterward. If you find that it's very confused to you, and then you can take a look on the coming example where I try to compare your results in Chinese, English, Math, and LS directly. For example, you see you have 59 in Chinese, and the mean x bar is 54. And you can see definitely you are doing better to the average, but how good, how better it is. And we can use standard score to do so, which is x minus x bar divided by sigma, which is 2. And next you got like 2.5 mark in Chinese. This is called standard score of Chinese. Next, we take a look in English, 52, but the mean is 57. And definitely you will see you are doing poorer than the average of the whole form. And now the standard score becomes 52 minus 57 divided by 5, which is the SD, which gives you a negative 1. So somehow now can you recognize or find that if you are doing poorer than the average, that means you will be getting a negative standard score. Afterward, you have Math 71, mean 69, doing better than average. But if you compare with the dispersion of the whole form, it's called 10 marks, which gives you 0.2 only. And you will see in this case, you can compare your relative result in Chinese and math, because in Chinese you're doing better because you've got 2.5 standard score, while in math you only have 0.5. So standard score in this sense give you a kind of like same ruler to compare your results in different subjects. And finally, the special case would be if you get the same result to the average, then because of the denominator is 38 minus 38, x minus x bar. So whatever SD you have in your form, and you will get 0. So 0 mark in standard score means that you are getting the exact mark with the mean. So finally, you will see this girl is called Kathy, and she is doing Chinese the best among the 4 core subjects. It's quite easy, right? And then so let's try to do example 21 and some exercise in the book so as to uh, understand the formula, use the formula in a more better way. The next application of SD will be on a very special distribution we call normal distribution. It's a very important idea in statistics, especially for those who are studying M1. But anyway, we will find that when we are talking about some measures in the whole world, for example, like IQ, maybe like height, maybe like, I don't know, maybe weight, or like your shoe size. And so for all this data, it fall into a normal distribution. So let's take a look on the um, features about normal distribution. First of all, you have a normal distribution curve like the one as follow. It is bell shape, we call it bell shape. You will see most of the data fall into the middle, where you will see it is the mean. This time we use the notation called mu to represent it. But indeed, so it is the value x bar or the notation x bar you used before. Anyway, it is the mean where most of the data fall into. Next to each side, less than the x bar and larger than the x bar, so it drops kind of maybe significantly or drops at two ends until it's getting closer and closer to zero. If you consider it's like an IQ normal distribution curve, it will be like this. For example, I've checked the internet and then so the research or the result telling me that in the whole world, most of the many people fall into the average IQ, which is 100. And then next, there are fewer people to get very high IQ. For example, if your IQ is 115, it's very high already, and then so the curve drops significantly until you get 130, you're genius already. And then so there are only few people which is getting IQ 150 or more, and then so this is one side. On the contrary, you have there are some people which is not very clever, and then so maybe drop to 85 in this case. And then if they are mentally disabled, and then the IQ will drop significantly, but the population is not very high. For example, you can check the definition of mentally disabled in the internet. It may be below 70 or below certain results, and then so hopefully it will be a very simple demonstration of what's the meaning of normal distribution curve as follow. And so we say it's very special, it's very important because in normal distribution curve or normal distribution, we find there are lots of special features, not about the shape, which is definitely you will see that it's not reflection symmetry as a metric because so along this dotted line, which is the mean, left hand side, right hand side, there's a metric. And the most important thing would be at this point or at this line, it's not just showing you the mean, but it also shows you the median and mode as well. So all the central tendencies fall into this line. This is one of the biggest feature. The second biggest feature would be we have said is about sigma, about SD. So how does it relate to? That's very magical. And at this line, the middle one, which is your mu, that means your x bar, the mean. And then we find that if it's a difference of 1 SD, that means it's mu minus sigma and mu plus sigma. And we find that they are totally 34% and 34%, totally 68% within this range. And then so it helps us to do a lot of statistical research or findings afterward. Next, we come to the second SD, which is mu minus 2 sigma and mu plus 2 sigma, 2 sigma. Then there will be 13.5% more, 13.5% more on two ends. followed by next mu minus 3 sigma and mu plus 3 sigma. There will be 2.35%, 2.35% more on both sides. So that's why sigma SD will be very important in statistics, because you see one of the use in normal distribution here. And then so up to 3 sigma, you will see that it's almost cover 99.7% of the whole population. This is the figure you will find in the normal distribution curve. And then coming up next, we take a look on how we will find, or how we use these percentages to help us to do some statistical findings or finding the results, etc. And then so let's take a look into the example 22, which is about the foot sizes of a group of children. And there should be some keywords to notify you it's about normal distribution, which is normally distributed, or like example 23. So it also tells you normal distributed. It is the keyword which tells you what you're going to do. And then now going back to example 22, you have the mean. That means the mu will be 20. SD, sigma, will be 2.5. And then the calculation is quite easy because it's asking you percentage directly. For example, so now you are going to find the percentage of children having their foot size between 15 to 22.5. So the first job you have to do would be you have to recognize how these two numbers related to mu and sigma respectively. Okay, so let's start from 22.5. You see it's mu plus sigma, and then while 15 will be mu minus 2 sigma. If you can recall the percentage for a while, then it's pretty easy, or else you may draw the bell shape, which helps you to do the calculation. So you do remember the dotted line will be mu, which refer to the mean. Now after our study, we find that 22.5 will be mu plus sigma, in which there are 34% of data fall between them. And then if you talk about 15, which is mu minus sigma, and afterward you have mu minus 2 sigma, you should have 34% as well as 13.5% respectively. So that's why the percentage now will be a simple percentage. So the percentage now would be simple addition, which gives you 34%, 34%, and also 13.5%, which total gives you 81.5% directly. The question can be further modified to be, for example, in this kindergarten, or for example, there are 1,000 children. Then in this case, if you want to ask how many children are having foot size between 15 to 22.5, then you can multiply 1,000 to the result, 81.5%, and finally you've got 815 children having the size of the foot in this range. Okay, so let's take one more example and have a look. Now we have a percentage of children having foot size less than 12.5%. And once again, we want to see what's 12.5% relate, how does it relate to mu and sigma. And you find that it's mu minus 3 sigma in our calculation. So what does that mean? So you have mu here, mu minus 3 sigma, that means, okay, mu minus 3 sigma is the data as follow. You want to know that it's less than 12.5%, that means the very little population on this side. So as a result, the percentage will be, so you do the subtraction one by one. And first of all, you have 100% in total. The right side is not counted, so minus 50%. While the red region, you have totally a difference of 3 sigma, including 34%, 13.5%, and also 2.35% respectively. So finally, you've got 0.15% for this very little population. Easy, right?